Let's try again. Let's try this. How are we doing now? Oh, bravo. So, Virgulator is a super genius idea. This is a microcontroller implemented completely in JavaScript. So this is actually. Do I get a mouse? Do I get mouse motions? Really cool. So let's see. Let's see. Who here is seeing a microcontroller for the first time? Yeah, I can't show you the result of the poll because yeah, but okay. So it's new for you. This is a really cool tool. Can you see it? Can just say something if you can see the Virgulator. Okay, some of you can see it. Okay, the rest of you can just open the URL and just open the URL if you're stuck. You know what? There's a screenshot also. So this is a microcontroller. It's a real implementation of a Virgule microcontroller. It's a variant of RISC-V. It has a very small instruction set. So yeah. So let's see what we see here. So on the left, there is the memory. There I can edit the memory. And you see there is a program memory. There's quite a lot of memory. This is a 32-bit controller. And I can change the function, and this is interpreted as machine language. And there aren't many machine language instructions for the regulator. So just to explain, this is add immediate. This is load unsigned immediate, uint immediate, and this is load bytes, and u is not immediate, and then this branch is equal. And this function JAL x0 is 0. That's just a loop. This function, what this is doing. Here's a simple program. This program is going to output all of the ASCII characters, starting from 32 and ending in 107. So when you write to, you see that X2 contains C0. So you write something to C0, it goes to this screen, the screen on the bottom. So I can just run it, and you see that it's just printing out all of the strings in the ASCII character set, and I can reset. So this is a microcontroller. Let's see again what's going on here. So this is the memory, and this is actually the chip. This is the microcontroller chip. So what do we have here? We have here the arithmetic logic unit. This is the part of the chip that actually does stuff. It can do computations, so it can do add, subtract, and so on. And there is a comparator, which is it does compare. And there's a bunch of general purpose registers. These are this is the internal memory, the internal variables of this chip. And there's a program counter. A program counter points to the position in memory of the next instruction that the microcontroller is going to run. And so now let's go over this program. And now I can turn on the animation feature. And I'm just going to let it run a little, and then I'm going to stop and go through it slowly. So you see that there is stuff coming from the bus, going to the instruction register, and then going to the arithmetic logic unit, and then it's going to here, and then the program counter runs, and then you write to the bus, and then all sorts of things happen. And I want you to pay attention to this row on the top, which goes through fetch, decode, and this is execute, and then you update the program counter. So now let me stop this animation, and I'll go through this program very slowly. So this program is going to output all the ASCII character set to this screen. See, if you write something to 0, this screen. So the first thing I'm going to do is my program counter is set to 0. I need to find out what is the next instruction that I should be executing as the microcontroller. So the program fetch, I'm going to write to the memory I'm going to try to read from the memory. So I'm going to say, please give me what is written in the memory in address 0. And then the memory chip sees this, and the memory chip outputs C0, this value. If you see the ending, the order is different. The C0 is here and C0 is here. So this goes through the bus and is fed into the instruction register. So I fetched the next instruction from the memory. Now the next thing I need to do is try to understand what is this instruction. So I do something called decode. Decode says, okay, this function means it's load unsigned immediate, and the value of immediate is C0. And what I need to do now to execute it is this. I take this value and I write it. I want to write it to the register. So the next thing I do is writing to the register. Okay. And now I need to find out what is the next instruction I want to execute. And this wasn't a branch or a jump or an if. So I'm just going to go to the next one. I'm just going to go to PC plus 4. You see? So now the next function is PC plus 4, and I'm going to fetch it from memory. I'm telling the bus, I'm telling the memory controller, give me this, and I'm going to get it from the instruction register. I'm going to decode it, and I'm going to. Now this is just add, so this is add. This is the result. The result is, so 0 plus 20 is 20 hexa, and I'm going to write it to another register. And now the next instruction is again. So I just want to go through one more because branch if equals is actually conditional. So I'm going to fetch and execute this one. And I'm going to decode it. And I'm going to add. So this microcontroller doesn't have a move. It has a very small instruction set. So you add something to 0 instead of moving. And then I just write it, and then I go to the next one. So now look at this one. What is this function? What is this line of code designed to do? BQ is branch of equals. Branch of equals says if x5 is equal to x0 to x6, then I'm going to jump 16 ahead, which is actually going to bring me to this. This is stuck. This is stuck in a loop. So if it's equal to 127, I'm going to get stuck in loop because my program has finished running. Otherwise, I'm just going to go to the next instruction. So now I'm going to fetch this from memory, right? And I'm going to decode it. So I know that this is an equals. I need to equal. So I'm going to compare x5 and x, right? I'm going to compare x5 and x6, and because they are unequal, I know that my next instruction is going to be, I'm not going to take the jump, so I'm not going to take the jump, which means that I'm just going to go to the next instruction. So this is a microcontroller, and I can run it for you. You see, it's going to do all these things, and it's really, really cool. I don't think you can boot Linux on this JavaScript implementation, but there are JavaScript microcontroller implementations which can boot Linux, which is kind of crazy. Yeah, I keep it running, and let's just reset it. So this is the Virgulator. Was this interesting? Because this is the first time was this an interesting experiment for you? This Virgulator? It's the first time I'm using it. I just hope it's not going to be deleted for some reason, because it's just a piece of JavaScript with no explanation and no comments, and it's self-contained. You can download it and so on. Okay. Yeah, you can copy it. Actually, if you press a little link key there, you can get a self-contained. If you just paste it into your browser, you get the program which is running. It uses a data URI. So now let's go back to my screen, which is going to be this one. So I showed you the Virgulator. And then I'm, of course, this is an attack course. It's not a computer architecture course. And I want to attack a microcontroller. And I want to use the fantastic shared whiteboard feature. And I want you to tell me where would I be getting the best measurements as an attacker? If the regulator is running something, where will I get the best power trace? So okay, so I see people are going to the arithmetic logic unit. So the arithmetic logic unit, let's say the arithmetic logic unit is doing a lot of interesting calculations, but it is a combinational circuit. It's a combinational circuit. So it means that it's not switching at the same time every time. So it wouldn't be so easy to measure. So somebody here is circling the register file. So the register file obviously has a lot of very interesting data in it, but it's very close to the ALU, and writing to it is not very power intensive. But I see that somebody here, okay, so everybody is going to the last thing which is circled. So the bus, yes, the bus. So what is this bus? The bus is a very, very long line which connects the CPU to the memory. And when I want to read something from memory, the CPU is going to write the address to the bus, and then the memory is going to write the data to the bus. When I want to write something to memory, the CPU is going to write both the address and the data to the bus, and then the memory is going to read from there and set the value of memory. And now this bus is very physically very, very long. So it has a lot of ice cafe inside it. It takes a large amount of power to charge and discharge it. And in fact, this bus, as a side channel analyst, is going to be the thing I see the most distinctly when I'm doing my power analysis, my power measurement. And if you think about it, you're getting a lot of nice data on the bus. Maybe really cool. They don't have AES here in the regulator. But we'll talk about microcontroller implementations of AES purposes. So it's the bus. The data is in the bus. Now, the bus has two sets of lines. One of them is called the address bus, and the other one is called the data bus. So the address bus says where in memory am I addressing, and the data means if I'm reading, the memory puts the value of the memory in the data bus, and if I'm writing, then the CPU puts the value of the value point to write in the bus. So the address bus in this specific microcontroller, of course, there are all sorts of crazier things. Only the CPU writes to it. But the data bus, both the CPU and the memory need to share it. So how can they share? How can two components share the same bus? How does that work? So what happens is that every time one of the devices, the CPU or the memory, isn't actively writing to the bus, it does something which is called pull-up. It holds it to the value of 1. So it's going to be this bus is going to be all ones, the data bus, all ones. And if you want to write, you just pull down the bits you need to pull down. So if I want to, if the CPU wants to read from the bus, it's going to set its output to high. It's going to be all 1. And then the RAM is going to pull down the value that it wants to change to 0. Once we're finished reading, the RAM is going to release the bus. It's going to let the values go up again. And then if the CPU wants to write, it's going to pull down the values it wants to pull down. And this is, by the way, the reason that we get Hamming weights in microcontrollers and not Hamming bits. If you think about it, the value of the bus is usually all ones. It's not dependent on the previous value. It's only dependent on the current value. So The microcontroller, if you're looking on the bus, you're not going to use the Hamming distance model, but you're going to use the Hamming weight model. And I think it will be more easy to see when we actually look at microcontroller power traces, as we will do hopefully later today. Mhm. So can we measure who is trying to read? I guess so. I guess so, yeah. It will probably look different. But I think you can also kind of understand from the context who is reading and who is writing. Yeah, you can do that. But usually, not say usually, but if you're talking about AES, as I'm talking about it now, AES has a very, very uniform structure. And you basically know what is happening. You know the instructions. They're not a lot of instructions. They're being done in a very structured way. You're only curious about what is the data. But if you're using something kind of more random or time-dependent function, then yes. Okay. So now let's look at the next slide. The next slide, I think I told you already. So the power consumers on microcontrollers are the buses, and the longer the bus, the better. So the bus between the core and the cache might leak a little, but the line between the cache and the RAM might leak much more. So the longer the bus, the better, and the higher the fan out. So if many components are connected to the same bus, again, more ice cafe. So again, it takes more power to toggle. And because the bus is set to 1, set to 1 between operations, the power consumption model is going to be Hamming weight and not Hamming distance. Okay, so if I'm writing 4 to my bus, let's say I have an 8-bit bus, I'm writing 4, so it's going to be all 0, all 1s, and then I'm going to lower all of the bits except of 1 because I'm writing 4, so I have 7 bits going down, and then it's going up again. If I'm writing 4, 5, 6, it's going to be all the bits down and then up again, and then 2 bits up and up again, and then 1 bit up and up again. So 4, 5, 6. So in all cases, it's going to be Hamming weight and not Hamming distance. But again, I'm going to show you a real trace so you can understand this. So I think we're ready to do some power analysis. Let's get some keys. So the figure I'm going to show you